Hi, good afternoon and a big welcome to everyone. Thank you for joining us at this webinar with the topic YugabyteDB and Immersive Indulgence on Distributed SQL. Our session today will delve into the architecture of YugabyteDB along with its cloud-native distributed SQL characteristics. Kindly post any questions that you have into the Q&A box below. Our speaker will try his best to answer them after the session. We also have a few interesting Yugabyte merchandise to give away to some lucky winners. So do stay tuned and check our chat box for more updates. Without further ado, I would like to introduce Mr. Srinivasa Vasu, our Senior Developer Advocate, to commence the webinar. Take it away, Srini.
Thanks, Laila. Hello there. Good morning, good afternoon all. Hope everyone is able to see my screen. This is second of a series of webinar that we are running in an APJ-friendly time zone. So today's session is on an immersive indulgence on YugabyteDB. I'm a solutions engineer with Yugabyte, so let's get started. Yeah, quick recap on what we looked at in our previous session, right? So in the previous session, we looked at what is distributed systems in general. And then we also looked at what, why, and how aspects of distributed SQLs and some of the key tenets of distributed SQL, like SQL compliant distributed storage, query processing, transactions, and strongly consistent replication, right? In this session, we are going to focus entirely on YugabyteDB. This session is going to be a kind of deep dive on all these characteristics and principles that pave the foundation of what we know as YugabyteDB today. I don't have any PowerPoint presentations per se, but what I've done is I've scribbled something in Miro. That's what you're looking at. This is just to give you a perspective of what I'm going to talk about, right? So I hope that at least this would help you to visualize in terms of the characteristics and features that I'm going to walk you through in the next couple of minutes or so, right? The first of the session will focus on the core concepts and the principles on which YugabyteDB has been built. And in the second of, we'll try to look at all those things through a live demo, right? So we'll see it in live action. I hope the live demo gets through without any issues, right? So what you're looking at in the frame, these are some of the key characteristics, some of the core tenets on which YugabyteDB has been built, right? For example, if you look at draft consensus, draft as the distributed consensus, YugabyteDB uses draft distributed consensus not only for leader election, but also for strong data replication as well. And in addition to that, draft has been used under the hood for other purposes as well, but that's for a different session, right? So in this session, we would focus more on how draft is being used for leader election and strong consistent data replication. And then we'll look at the relationship between replication factor and fault tolerance. What role does replication factor play in terms of ensuring high availability of the system? What is the formula that underpins between replication and fault tolerance, right? So in the sense, what is the right replication factor with which we need to create a Yugabyte cluster so that the cluster would be able to continue to serve your read and write traffic in spite of one or two replicas going down in the system. And then we look at the significance of placement policy. What role does placement policy play in terms of seamlessly sharding and distributing your data across various fault domains in the system, facilitating things like distributed transactions and asset, at the same time ensuring that the database itself is highly available in spite of the fact that YugabyteDB favors. I think my sharing window is gone, I guess. Some power cut. Apologies for that.
We can see your screen now, Srini.
Yep. Apologies for that. And the last thing is we'll look at the significance of placement policy. What role does it play in terms of sharding, automatically distributing your data across various fault domain, ensuring that the high availability is taken care of, even though YugabyteDB as a system favors consistency when it comes to cap theorem. All right, let's get started. Okay, so when it comes to Raft, on a high level, YugabyteDB under the hood uses Raft for leader election and data replication. So what you see is the gist of it. So in a Raft group, you'll have n number of instances that would participate in an election process. Through the election process, one of the nodes would be elected as the leader, and rest of them would be the followers, and then it would continue to interact with the leader in the system, right? So the leader in the group would continue to send heartbeat information to rest of the followers, letting them know that it is still alive and it's doing the role of the leader, right? In case if the followers fail to receive heartbeat information from the leader, then one of the followers would get promoted as a leader, as a candidate, and then it gets into an election process, and then it becomes the leader, right? So let's look at how the leader election happens in Yugabyte through Raft consensus protocol, right? As I said, in this case, time plays a critical part in any distributed system. Everything is based around time, right? Time is one of the core key tenets, right? So in this way, when it comes to Raft, there is a timer that runs in every node that gets timed out, and basically it's randomized across the nodes in the Raft group, right? So even if two nodes if the timer in two nodes, gets timed out at the same time, then again it gets into the retiming process because it's randomized across the nodes. The next time it won't, no two nodes will conflict or would get timed out at the same time. What happens through this election process is once this timer gets timed out in the node, then one of the node becomes the candidate, and then it gets into this election process. That's what you see here. It initiates this election process and the term becomes one, and this node votes for itself. And then at the same time, it requests for votes from rest of the nodes in the Raft group. And when rest of the followers receive the request, it would look at its own internal term. So in this case, the term is 0, so that it's eligible to vote for this new term 1, right? The followers can't vote more than one node in a given term. So that's the reason it has to validate whether it has already voted for this term, or this is the first time it's voting for this election term, right? So it looks at its internal state, and the term is 0, so that it gets incremented to 1, and then it votes for this term. And that's how the rest of the nodes in the Raft group would react to this voting process as well. Once this node which sends out this voting request to rest of the nodes in the group, once it receives majority of acknowledgement, so the rest of the nodes, once the rest of the nodes in the group acknowledges to this request that, yeah, I'm happy to be elected you as the leader, so that you'll be able to perform the role of the leader. So once it gets the majority of votes from rest of the nodes in the group, it becomes the leader for this term, right? So that's how the transition is. So initially it starts with term 1, vote 1 when it votes for itself. And then once it starts receiving votes from rest of the nodes in the group, the number of votes would get incremented. And then once it has the majority of votes, it becomes the leader. And rest of them would be the follower in the Raft group, and the leader would continue to send heartbeat information to rest of the nodes in the system. So that's the leader election process. So when it comes to Yugabyte tagging uses Raft for strong data replication. In addition to these two core things, Raft has been used for other things as well, like leader leases and a few other things. But we are not going to focus on those things in this talk. Rather, we'll leave those things for the next session, right? So when it comes to data replication, so imagine a case here: the client is connected to the leader, and client sends a request to this leader, set this value for this entity, right? So set 20 is the value for this entity. So the request goes to leader 1, and then the leader 1 processes the request and writes the data to its local copy. And at the same time, the leader synchronously replicates the data to the followers as well, right? So letting the followers know that I've received this request, this is the value needs to be replicated, right? So once the followers receive the request, and it again writes the data to its local copy, and then it acknowledges back to the leader about the successful receipt of the data, right? So once the leader gets the acknowledgement from majority of the nodes, then the leader commits the data. Leader commits the data to its local file system that this has been replicated successfully to rest of the nodes in the raft group, and it sends the acknowledgement back to the client. At the same time, lets the rest of the followers in the raft group know that it's time for you to commit the data to the file system as well, right? So that's how the data replication works, right? So every time it gets a request from the client, it writes to its local copy, and then it sends the same request to the rest of the nodes in the raft group. And once it gets the acknowledgement from the majority of the nodes, the data gets committed, and then the acknowledgement is sent back to the client. And as part of the next heartbeat or next append entry, the same information is propagated down to the rest of the nodes in the system as well. And imagine that if this node crashes for some reason, so the leader crashes or the node itself is not reachable, then one of the followers would become the leader. And when it becomes the leader, it would still have the most recent write to be returned to the file system. That's how we ensure, that's how Yugabyte ensures strong consistency via raft replication, right? And the next part is what is the relationship between replication factor and fault tolerance, right? So in the previous slide, we looked at a raft group of 3 nodes. That is essentially determined by this replication factor. When you define your replication factor as 3 at cluster level, then each group would have three parties would be getting into this raft election process. And those 3 entities would be responsible for data replication as well, right? And those 3 entries would work in a quorum. As long as the quorum is intact, the system is going to function. It would continue to serve your read and write traffic. So what is the formula that underpins it, right? So basically the formula is 2n plus 1. So for example, to have a system with a fault tolerant of 1 node, right? So to withstand a failure of 1 copy, the replication factor has to be 2 into n plus 1, right? So in this case, to withstand a failure of 1, so you need to run with the replication factor of 3, right? So to withstand a failure of 2 copies, then the replication factor has to be 5, right? So meaning that your system would continue to operate, would continue to serve read and write traffic as long as 3 out of 5 copies are healthy, right? So you can afford to lose 2 replicas out of 5, but at the same time, the system would continue to operate without any disruption, right? So that's a relationship between replication factor and fault tolerance. In the case of distributed system, especially in YugabyteDB, replication factor plays the major role. That's how we ensure that data has been replicated and the quorum is maintained. And as long as the majority of the nodes are healthy, reachable, able to communicate with each other, the system would continue to serve read and write traffic, right? So the next important factor, this is to understand the placement policy, right? What role all these things play, right? So we looked at raft, how raft has been used in YugabyteDB, and then we looked at replication factor and fault tolerance. The next important thing is placement policy, right? When it comes to YugabyteDB, essentially it's broken down based on these 3 entities: cloud, region, and zone, right? So cloud is the parent level entity. Within a cloud, you can operate across multiple regions, and within a region, you can operate across multiple zones. So that's how the relationship is established, right? And that's how the data would get distributed. That's how the cluster would get distributed. Nodes in the cluster would get distributed, and so on and so forth, right? On the right, what you look in the frame, it's more about different kinds of deployment patterns, right? Single zone deployment pattern, multi-zone, multi-region, and multi-cloud, right? And each deployment pattern uniquely defines the fault tolerance, right? In the case of single zone deployment pattern, the distribution would be within a single zone, right? So that's what you see here. The cloud entity is YB cloud. Within YB cloud, the region is AP South 1. And within that AP South 1 region, the zone is AP South 1A. So when you create a cluster with 3 nodes with the replication factor of 3, each node, all 3 nodes would be placed in the same zone, AP South 1A. And this becomes your single point of failure. So if that zone goes down, then the cluster is going to be non-operational. So that's a single zone deployment, right? So in order to withstand zone level failure, you have to look at the next level, which is multi-zone, right? So in this case, zone becomes your fault domain, right? You need to ensure that the data has been replicated across various fault domains, right? So to withstand failure of a single fault domain. So when it comes to multi-zone deployment, look at the last entry here. So AP South 1 is the region. Within AP South 1, we have 3 AZs here. AP South 1A, 1B, 1C. There are 3 AZs here. So when you create a cluster with 3 nodes, each node would be placed in 1 AZ, so that 1 copy in 1A, 1 copy in 1B, and 1 copy in 1C. So in this case, you'd be able to withstand one fault domain failure, right? So that's what the formula says, right? So if the replication factor is 3, you would be able to withstand one copy failure. So if the entire zone goes down in this case, if AP South 1A goes down or one of the AZs goes down, still the cluster would be operational, it would continue to serve read and write traffic, right? So if at all if you want to withstand region level failure, right? So in the case of multi-zone, your region becomes your single point of failure. If you lose the entire region, in this case AP South 1, then the entire cluster is going to be non-operational, right? So if you want to withstand region level failure, then the next is multi-region deployment, right? So where you would create a cluster that would get stretched across multiple regions, right? So in this case, it's across AP South 1A, AP East 1, and EU West 1, right? So that if one of the regions goes down, let's say AP South 1 or AP East 1, as long as the other two regions are able to communicate and healthy, your cluster would continue to serve read and write traffic. In this, and the next one is the multi-cloud, where you would be able to serve a cloud level failure, which is very rare, by the way, right? But essentially, that's the role of placement policy. So once you define your placement policy as part of the cluster creation, any data that gets returned to the system would get distributed based on this placement policy, right? So this is like infrastructure as configuration or database as configuration kind of information that gets defined at cluster level. And under the hood, Yugabyte makes sure that whatever your desired configuration that you have defined as part of this, the actual is always in line with your desired configuration, right? That's the significance of placement policy. And the next step is we understood that YugabyteDB inherently distributes your data across nodes, across different fault domains, and so on and so forth. How does that distribution happens, right? How does it do sharding under the hood, right? So sharding is a technique which what essentially does is basically a single table is being broken down into multiple slices, and YugabyteDB uses two different algorithms in terms of distributing your data. One is based on hash, another one is based on range. So in this session, let's look at hash. But under the hood, range applies different technique. But once that technique is applied, the data is going to get a single table is going to get sliced into n number of shards, and it's going to get distributed across, right? What you're looking at in the frame is it's a table with n number of rows and columns. And in this case, this is a table named T and K being the primary column, and you have other columns as well, B, B, C, D, right? And when it comes to hash sharding, what it does is hash uses a 16-bit key. Basically, it's a 16-bit key that spans from 0 cross 0, 0, 0, 0 to FFFF, right? So it's an hexadecimal representation. 2 power 16 would give you this range, right? So when you apply hash sharding, what it essentially does is it basically computes this hash value for your primary key. So in this case, it would compute the hash value for your primary key. And based on the hash value, it would place your data in the appropriate shard, right? So in this case, from an understanding standpoint, I've applied a 1:3 split, meaning that a single table has been sliced into 3 different shards, shard 1, shard 2, shard 3. Again, the entire range has been split across all 3 shards, right? So 0 to 5555, and then 555 to AA, and then all the way to the upper limit of the 2 power 16 value, right? So it's a 1:3 split, but essentially the split is based on the number of compute and other techniques. You'll be able to override the split as well. But from an understanding standpoint, let's stick to this 1:3 split value, right? So if you apply the same thing to the table that we have taken as a reference here, so basically it computes the hash value. Again, the hash value is in hexadecimal representation. The hash value of 87 is 90 FA. And appropriately, it will find out the hash value for the rest of the other keys. And based on that hash value, it will find out the range, right? So shard 1 holds this range. So if the hash value happens to fall in this range, then the data is going to get placed in this shard, right? And that's how it gets applied to the rest of the rows in the table, right? And the sharding is going to be based on this technique. It doesn't matter whether you have 15 shards or 20 shards or whatever it is. And it's going to compute that hash value for your primary key. And based on that hash value, wherever the primary key fits into, and the data is going to get sharded into that specific shard, right? Based on this range. So now we bring in, if you bring in all those constructs that we looked at, right? Placement policy, replication factor, wrap, and all those things. So the placement policy says that in a cluster of 3 nodes, which is distributed across 3 availability zones, AZ1 and AZ2, make sure that the data is equally sharded, right? So if I bring in my replication factor into play, so replication factor of 3 says that each shard should have 3 copies. So that's the reason you see here AZ1, node 1, which is placed in AZ1, has got 3 copies, has got 3 shards, shard 1, shard 2, and shard 3. As the replication factor is 3, that means shard 1 should have 3 copies in the cluster, right? So that's the reason you get to see shard 1 in AZ2, shard 1 in AZ3. In a similar way, all the nodes in the cluster, since the replication factor is same as the number of nodes, each node in the cluster is going to hold the complete data set. So the total number of shards in the system is 9. So a single table has been split into 3 shards. When we apply this replication factor of 3, there will be 3 copies per shard. And the total number of shards is going to be 9, right? So that's the number of shards in the system. If I bring in Raft into play, Raft says that out of 3 copies, 1 would be the leader, and the responsibility of the leader would to serve your read and write traffic, right? So out of 3 shards, shard 1 in node 1, node 2, and node 3, 1 is going to be the leader. And these leaders are going to get equally distributed across your fault domains, right? So if that, because we have applied placement policy in such a way that make sure that whatever the data that gets into the system, it's spread across my fault domains, and the leaders need to be equally distributed across my fault domains. So that's the reason you see 1 leader per shard. So essentially 3 shards, there has to be 1 leader for each of the shard. So node 1 being the leader for shard 1, and appropriately node 2 and node 3 are hosting other shards, other shard leaders in the system, right? So total 9 shards, 3 shards per node, and 1 leader per node, right? So that's how the sharding mechanism works within Yugabyte, right? So in this case, we looked at the sharding mechanism for 1 table, but if you have 10 tables or 100 tables, those entities are going to get sharded based on this logic, and that's how it's going to get distributed. And at any given point of time, you would find multiple shards in the system, and each node hosting n number of shards plus shard leaders as well. So that's how it facilitates distributed query processing, and then each node in the cluster would be able to serve read and write traffic, because if the data that you're sending to the system is for this shard, then AZ1 is going to process your request, and if it's need to be if the data needs to be returned to shard 2, then AZ2 is going to process your request, right? So that's how it ensures all the nodes in the cluster are able to seamlessly process your read and write traffic. And moving on to the next part is partition. There is a subtle difference between partition and shard, right? So in a distributed system, you'll find at least 1 shard plus 1 or more shards, but there is no, I mean, and when it comes to partition, distributed system may have 0 or more partitions, right? So partition is more of a declarative construct at the query level, whereas shard is the physical slice of your data that resides in your underlying file system, right? So when it comes to Yugabyte, also it supports Postgres declarative partitioning API. So in the frame, what you're looking at is a table that's defined, it's named racing, and it's been partitioned based on range, right? So it applies a range-based partition, and it's been partitioned based on this column called calendar year, right? So define all the data in calendar year racing underscore 2021 in this table. So if the range is between January 1st, 2021 to December 31st, 2021, then the data should get into this shard. Whereas if it's for 2020, then the data should go to racing underscore 2020 table, right? So this is at the API level, right? At the API level, we have defined a table named racing, and then racing has been partitioned by range based on this calendar year into 2 different tables, right? Racing 2021 and racing 2020, right? And when it comes to Yugabyte, again, the same technique applies, right? So whatever we looked at it for single table name key, the same sharding mechanism at storage level gets applied. So essentially, raising underscore 2021 would be a table in Yugabyte, and raising underscore 2020 itself is a table in Yugabyte, right? And if you apply the same 1:3 split, then raising underscore 2021 is going to get it's going to split into 3 shards, and same is the case for raising underscore 2020, right? And then if I apply the placement policy, it says that it needs to be distributed across all nodes in the cluster. When I bring in that replication factor of 3, then we have now 2 tables, and each table has got 3 shards. So that means all these shards are going to get distributed. And the replication factor is 3, which says that there has to be 3 copies per shard. So essentially 6 into 3, it's going to be 18 shards, right? So in total, you'll have 18 shards in the system, out of which 6 shards per node, right? So that's what the policy says, that needs to be equally distributed. So when I bring in raft into this now, then there will be tablet leaders for 3 copies of the raft group. So partition 1, shard 1, partition 2, shard 2, the leaders are placed in node 1. In a similar way, the leaders for the rest of the shards would be placed shared between node 2 and node 3, right? So essentially, when you look at the system, each node will have 6 shards and then 18 shards at the cluster level, and each node would host 2 leader shards, right? So that's the 6/2 number indicates the total number of shards per node is 6, out of which 2 are the leader shards, right? So that it would serve read and write traffic for the corresponding shard related operations. So the next part is the fault tolerance, right? So this is the important thing, right? So we spent time in the previous scribble to understand what raft is, replication factor, sharding, and how it gets distributed, and how the leaders are elected, and so on and so forth, right? So when it comes to fault tolerance, so the clients can be connected to any of the nodes in the cluster. So again, what you're looking at, this is a cluster with 3 nodes, stretched across 3 AZs, AZ1, AZ2, and AZ3. And you have clients connected to all the nodes in the cluster, right? So clients sitting in AZ1 zone are connected to node in AZ1. And in this case, all the nodes in the cluster are connected, so that it would continue to serve. It would serve read and write traffic without any disruption. Imagine a network partition, right? Which can happen in any distributed system per se, right? So if the network breaks down between node 1 and the segment at which node 2 and node 3 are deployed to, so if there is no communication between node 1 and node 2. Node 1 and rest of the nodes in the cluster, then clients connected to node 1 are going to get disrupted, right? Because as per the replication factor and fault tolerance formula, it says that the majority should be healthy, right? So when clients write to node 1, even though imagine that node 1 happens to be the shard leader, though it can process the request, but it can't replicate the request to rest of the raft group, right? Rest of the processes, rest of the nodes in the raft group, because the network is disconnected, can't replicate the data, right? So in such cases, what it does is it just backs off. It would tell the client that I'm not sure whether I can accept your request, because since I can't replicate the data to the rest of the followers, there is no way I would ensure consistency, right? Because Yugabyte favors consistency in a cap theorem standpoint. Whereas the nodes that are connected, clients that are connected to node 2 and node 3 would continue to get information, write information to the cluster, because the majority is intact there, right? So node 2 and node 3 are able to communicate with each other, so that there is no disruption, because 2 out of 3 nodes are intact. So node 2 and node 3 would continue to process read and write traffic, whereas clients connected to node 1 would get disrupted. In such cases, what we do is that if the clients connected to node 1, if those clients know about the whereabouts of rest of the nodes in the cluster, then you'll be able to handle it on the client side, so that you can connect to one of the surviving nodes in the cluster to get your transactions through. But that's a sort of heavy lifting that needs to be done on the client side, right? So In order to overcome this problem, what we have done is we have built something on the client side as a library called Smart Driver Capability. Essentially, what it does is this capability is built as part of the driver itself. So once clients connect using this driver to the cluster, the smart driver is capable of auto discovering all the nodes in your cluster. So it's cluster aware. So the number of nodes in your cluster. And in any distributed system, as you know, any nodes can come and go off at any given point of time. And the driver is intelligent enough to auto discover the topology related changes, right? Topology related changes. And at the same time, so if we look at the same failure scenario, if there is a network partition and if node one is no longer connected to the cluster, then smart driver would detect that failure, and then it would automatically reinitiate that invalidated physical transaction to one of the surviving nodes in the cluster, right? So whatever the connections that were established before, established to node one when it was healthy attached to the cluster, all those things would get invalidated, and smart driver would reinitiate those connections to other surviving nodes in the cluster, right? So in this case, the cluster is clustered. In this case, the client does not need to do the heavy lifting. The heavy lifting is automatically done by the smart driver for the clients connected using the smart driver, right? That's more on the client side when it comes to fault tolerance, right? And we just have to look at fault tolerance from a server side perspective as well, right? So what happens when one of the nodes in the cluster, gets disconnected? What happens to the data? Because data is essentially replicated across multiple nodes. So would that reinitiate a re-replication to other surviving nodes or not? Let's look at all those cases now, right? So when it comes to placement policy, so in this case, I was slightly altered our cluster topology. All along, we were seeing a cluster created with 3 nodes. That's been changed to 4 nodes now. The reason is I just want to cover 2 failure cases here, right? So those 2 things are important, right? So when would the cluster initiate that re-replication process? When would the cluster operate with under-replicated data, right? Those two things are important, right? So in this case, we have a cluster with 4 nodes. 2 nodes are placed in AZ1. So essentially, AZ1 has got 2 nodes to serve your read and write traffic, and AZ2 and AZ3, rest of the 2 availability zones have only 1 node, right? So in this case, the table split is 1:4. That's the reason you get to see 4 shards. Again, from a from an understanding standpoint, I just want to keep it simple. So S1, S2, S3, and S4. And if I apply the replication factor of 3, then we would see 3 copies of S1, and then you would see 3 copies of all the shards in the cluster, right? And the placement policy says that it needs to be equally distributed across my fault domains. So that's the reason you see AZ1 has 1 fault domain, right? And AZ1 has got 4 shards, right? So and you have only 2 shards per node, because it says that my copies need to be equally distributed across the fault domains. And in this case, the fault domain happens to be your AZs, right? So AZ1, AZ2, and AZ3. So that's the reason AZ2 and AZ3 have 4 copies. So 4 copies per AZ. And then the remaining 4 copies in AZ1 would be shared between 2 nodes in the cluster, right? So AZ1, node 1 and AZ1 would have the copy of S2 and S4. It could be different as well, but all that matters is out of 4 shards, it will have the copy of 2 shards, and remaining will be placed in the other node in the availability zone. So when you bring in raft consensus, then there will be one leader for the entire raft group. So S2, S2, S2 across 3 AZs, 1 would be the leader. So in this case, node 1 in AZ1 happens to be the leader for S2, and you'll find the copies of S2 in AZ2 and AZ3, right? So that's how it works. So let's go through all the failure cases that we looked at it from a client standpoint earlier. So if node 4 goes down, right? Imagine that node 4 crashes for some reason, whether it's a scheduled maintenance or unscheduled or whatever it is, right? Node 4 crashes for some reason, it's no longer connected to the cluster, right? In this case, what happens is it gets detected immediately, And node 4 is hosting the shard leader of S1, right? And node 4 is responsible for serving all the read and write traffics that go to shard 1, right? So that means that one of the followers would need to take the role of the leader immediately, right? So it gets detected automatically, and then S1 would move to one of the surviving nodes, right? So it could land in node 1 in AZ1, or it could land in node 2 or node 3. So in this case, it has landed in node 2, but essentially one of the surviving nodes would take the ownership, or one of the replicas would immediately take the ownership, and it would continue to serve your read and write traffic, right? And whatever the shards that were in node 4, S1 and S3, those shards have been successfully re-replicated now to node 1 in AZ1, because we still have one surviving node in AZ1. That's the reason it has re-replicated the shard process, right? The other failure case is what happens when both the nodes are down, right? What happens if I lose my entire availability zone 1? So in this case, the placement policy clearly says that my data needs to be equally distributed across my AZs. I started with 3 AZs in my cluster. Now I'm operating with 1 E2 AZs because my AZ1 is down. It's no longer connected, right? Maybe because of network reason or some power outage or whatnot. So the entire AZ itself is down. So in this case, the cluster would not initiate that re-replication process. So in this case, your actual state won't be same as your desired state. Instead of 3 copies, you'd get to see only 2 copies in the system. So this is one of the cases where you would operate with under-replicated copies of your replicas, because based on the policy, it has to make sure that the replicas are equally distributed. As you are now down with 1 AZ, the complete AZ itself is down. There is no point in replicating the data to AZ2 or AZ3, because it becomes a single point of failure, right? Because if you lose AZ2, even though it has 2 copies, if the AZ itself is gone, you're going to lose both the copies, right? So it does not make sense to again re-replicate the data to one of the surviving AZs, fault domains per se. Had one of the nodes been alive in this AZ, then it would have initiated that re-replication process. Since we have lost both the nodes, it's not going to replicate your data, right? All right, let's look at all those things quickly. Look at all those things in action, right? So I'll jump onto the terminal. Just give me a second. Okay, the extended display is not working. Let me continue with the same display. All right, I'm going to start my server now. I'm going to create a cluster with 3 nodes. So it's bringing up my cluster. Just give it a second. Yeah, if I go to 127, and then if I hit my cluster endpoint, I'm going to see the cluster, right? So we are going to look at all the cases, all those things that I explained to you through the Miro scribbles, right? So in this case, we have created a cluster with 3 nodes. So like what you have seen in the earlier slide, masters and T servers. Master is responsible for all the administrative related stuff. And the number of T servers is also 3 that is responsible for managing your data, right? So this cluster is empty because we haven't created any artifacts per se. So that's the reason user tables is empty. And you don't get to see any tablets or shards under the T server instances, right? So in this case, we have created a cluster with 3 nodes. Let's look at replication factor, placement policy, and all those things that I covered, right? The replication factor is 3, so that indicates that we need to maintain 3 copies of our data. And if you look at the placement policy itself, similar to what I explained to you, it's been broken down into these 3 entities: cloud, region, and zone. YB cloud is the cloud entity, and within that AP East 1, EU West 1, and AP South 1, right? So This is a multi-region deployment per se, and cloud remains same. It's all been deployed to YB Cloud. Under YB Cloud, we have 3 regions: East one, EU West one, and AP South one. And then within that region, we have a 1C, 1B, and 1A as the placement zone, right? So these two become our fault domain. So the combination of the region and zone would become our fault domain, right? And let's go ahead and create a table, right? So I'm going to connect to my Gigabyte instance, right? Zoom it up, right? Okay, I'm going to create my first table. So create table T. This is the table that we looked at. So if I go back to the Yugabyte UI console again, I'm going to look at, if I look at the number of user tables, the number has increased to 1 because since we have created a fast table, the table has been created in the system. And let's look at how the placement policy, replication factor, and draft related principles are being applied to this table, right? So in this case, the table is being split into, so it has applied the same 1:3 split. So that's how I defined it in the system, right? So I've defined it in the system in such a way that maintain 1 shard, or rather 1 tablet per node. Since we have a cluster with 3 nodes, each node is having 1 shard, 1 slice of the data, right? So the table T is being split into 3 tablets, and then it has applied the same replication factor as well. So, and it has applied draft-based principles as well. So that's the reason 127.0.0.3 is the tablet lead, is the leader for this tablet. And in a similar way, the leaders are also equally distributed across my fault domain, right? So 02 is in one FD fault domain, 04 is in one FD, and 03 is in another FD, right? And the other replicas are also maintained, right? So for this shard total, there are 3 copies. One is the tablet leader, remaining 2 copies reside in 0.4 and 0.2, right? And if I get into the tablet servers view, and this is the overall thing, right? So essentially, table has been split into 3, and the replication factor is 3. Total, there has to be 9 shards, and each node has got 3 shards, right? So if you count the overall number, it's 3 plus 3 plus 3. Total number of shards is 9. And then we have 1 shard leader per node, right? So that's the distinction. 3/1 indicates that each node has got 3 shards, and 1 is the leader for that shard, right? And then let's look at how partitioning works in the system as well, right? So I'm going to drop this table, otherwise it would be difficult for you to understand the shard count per se. So I'll drop this table, and then I'll apply the. So once I drop this table, if I go back again, it's going to be 0. So T server is going to have 0 tablet leaders and shards because the table itself is dropped. So if I go and apply the partitioning logic, so again, I'm creating a table, racing table, and it's been split into 2 partitions based on 2021 and 2020, right? If I go back to the console again, you're going to see the number of user tables is 3, even though it's 3, but essentially the base table is a logical reference to the actual partition itself, right? And then if I look at my tables, it would have applied the same principle. The partition itself would be interpreted as a table at the storage level. So tracing _2021 partition, which is the table that we created, is going to have 3 shards, right? So 2, 3, and 4. And similar to what happened for table T, it has distributed it across fault domains, and then the leaders are equally placed across fault domains as well, right? So if I go back to my tablet servers, the count would be the same. Essentially, you get to see 18 shards. In this case, 9 plus 9, 27. Because racing itself is a table, right? So though it does not physically hold any data, but from a metadata standpoint, it would still have 3 shards from a metadata perspective. So that's the reason the total number of shards in the system is 27, and each node is hosting 3 shard leader per se, right? So that's equally distributed, right? Let's drop this as well so that we'll look at all the failure related cases, right? So I'm going to drop these tables, and then it would be easy for us to understand. Otherwise, the shard count would be different. So you just have to run your maths in your head, right? So yeah, it's already deleted since I've deleted the table. So go back to the view. It's all going to be good. So let's look at the failure case, right? So I'm going to create a cluster now with 4 nodes. I'm going to increment it to 4. So instead of 3 node cluster, it's going to be a 4 node cluster. So if you look at the cluster topology now, so see full config, the number of replicas would remain the same, and it's the fault domain, it's still distributed between region and zone. And when it comes to the number of nodes, if I go back to my T servers, if you see here, I have, so AP South 1 is the region, and AP South 1A is the zone, right? It has got 2 nodes. So this is the fault tolerance case that I explained to you, where we looked at a cluster created with 4 nodes, out of which 2 nodes were in one fault domain, remaining 2 nodes were distributed between other 2 fault domains, right? So in this case, AP East has 1 node, AP South has 2 nodes, and then EU West has 1 node, right? So this is a cluster with 4 nodes. So now, since we haven't created any table, it's empty. So we go ahead and create my first table. I'll take this example, right? So SQL SH connect to the terminal, and then if I create my table, if I go back to the UI, so the table is already been created, and then if I look at my tablet service, you'd be able to see the difference, right? So so it's a single table that's been split into 4 shards based on the number of nodes in the cluster. Since this cluster we have created it with 4 nodes, so 1 shard per node. So that's the reason there are 4 shards for this table. And then in terms of the distribution itself, so is AP South 1, that availability zone has 2 nodes. So that's the reason the 4 shards are equally distributed between 2 nodes in that zone, right? So essentially 4 shards applying the replication factor of 3, the system should have 12 shards, 4 plus 4 plus 4, total 12 shards. And AZ2 EU AP East 1C has 4 shards, West 1B has 4 shards, whereas AP South 1A has 4 shards distributed between 2 nodes, right? So that's the difference. So let's look at the failure case. What happens if I bring down one of the nodes in the cluster, right? So I'll go ahead and bring down node 4, which is, in this case, I'm going to bring down 127.0.0.5, right? So if I refresh my view, everything is healthy. The heartbeat information is flowing across all the nodes in the cluster, so there is no disruption, right? So the moment when I stop my node, I'm stopping that instance. So if you look at here, the heartbeat information is going up in 127.0.0.4, whereas the leader is already been relocated to one of the availability zone, because earlier 127.0.0.5 was hosting 2 shards, and one was the shard leader, right? So when this node goes down, then one of the followers would take the leadership role immediately within few seconds. And because it would detect that the heartbeat is not flowing from the leader. So once it reaches the threshold and the failure count, one of the followers would become the leader, right? So in this case, the leader has been shifted to east. It could go to east or west, or it could happen in the same AZ itself, right? So in this case, it's been taken up by east because that's where the other replica was, right? And essentially, we would obviously expect the replicas to be re-replicated in other node in the cluster, right? Because in this case, we haven't lost the entire AZ itself. We have just lost one node in the AZ, right? So if I refresh my view again, so it would wait for a certain period. The default is 15 minutes or so. After 15 minutes, it would initiate that re-replication process. It would see whether if you have any surviving nodes in the daisy, If that's been the case, then the data would get distributed across the surviving nodes in the daisy. So from a demo standpoint, I've brought down the number to 60 seconds. Once that 60 seconds elapses, then the master process would automatically re-replicate the data to other surviving nodes in that availability zone. So that's why you get to see the count now. The total count is still intact, 4 plus 4 plus 4. That's what the desired configuration says, right? So you need to have 12 shards at any given point of time. You still have 12 shards in the system. And then the leaders are like 2 plus 1 plus 1. We have total four leaders in the system, right? So that's how it ensures that the data re-replication happens as long as you have surviving nodes in the availability zone, right? So if I bring back my cluster again, if I bring back the node again, if I come back and refresh my screen, see the node is added back to the cluster, and the data is getting replicated as well. And within a few seconds, now earlier 127.0.0.2 was hosting 4 copies of the data. Now it's been equally distributed between 02 and 05. In few seconds, it will become the tablet leader for one of the shards, right? See, that change has also happened, right? So behind the scene, the background process, the master ensures that the placement policy related information is kept intact at the cluster level, right? So runtime, whatever the changes that happen within the cluster, it does its best to equally distribute your data and the compute and the processing capabilities across nodes in your cluster, right? So quickly move on to the other failure case, which is the under-replicated scenario. So which is like instead of bringing down 05, let me go ahead and bring down 04, because this availability zone East 1C has got only one node. And at this point of time, it has got 4 shards and 1 tablet leader, right? So if I stop that node, quickly the leader has been shifted to 127.0.0.3. So that's the reason you see 4/2. So at this point of time, the expectation is to have 4 leaders, so 1 per shard, which is intact, right? So there is no problem there. And the heartbeat information is going up. There is a default time that's been configured in the system that after 30 seconds, the failure would get reflected in the UI, though it gets detected immediately in the backend system. From a UI standpoint, it gets detected after 30 seconds. Like similar to the last failure case, right? Where after 60 seconds, after that 60-second threshold elapsed, the data got replicated to one of the surviving nodes in the AC, right? But in this case, it won't happen because we have only one node in this availability zone, rather in this fault domain, right? So the 60 second is gone, though the replication count has gone down to 0. But if you count the number of replicas, the expectation is 4 plus 2, 6 plus 2, 8 plus 4. Total system should have 12 replicas as per the replication factor. But at this point of time, it's not having 12 replicas because you don't have any surviving nodes in that zone, right? So it's not going to re-replicate the data across zones, which is not going to give you any value add person. So this is the scenario where you would operate with under-replicated data. So once this cluster comes back, if I start that node again, then you get to see the count back to 12 again, right? So 4 plus 4 plus 4. Now it's again back to 12, right? So that's how it ensures that once the node joins back the cluster, or if you have any surviving nodes in the zone, it would do the rest for you, right? That's pretty much on the demo. So moving back to the Miro board, I think that's pretty much my last slide. So this is the high-level architecture. So this is the cluster that we created. We created a cluster with 4 nodes, with 4 tablets, 4 shards in the cluster with 1 shard per node, and so on and so forth. And YBT server is the one that's responsible for managing your data, and master is responsible for doing all the administrative related activities, like when you create a table, split the table into shards, and then distribute it across your T servers, initiating a re-replication process, initiating a backup and restore process, and so on and so forth, right? That's how YugabyteDB uses all the distributed SQL characteristics, key tenets, and the principles under the hood to get the job done. All right, that's pretty much from me. So let's look at, do we have any questions? I think we are right on time. So we have some time to go through the Q&A. Any questions?
So Srini, there was a question from Amol. I did answer that question, but yeah, go ahead and explain it slightly in detail. It's in the Q&A chat box.
Smart driver works at the client side affairs, then at the client side, a smart driver is configured automatically. Yeah. So smart driver is nothing but a client library. It's something similar to, I mean, if you need to connect to a Postgres service, you would use Postgres JDBC driver, right? And Yugabyte JDBC driver is built on top of Postgres driver with all those capabilities that I explained to you. So similar to how you would connect to Postgres using Postgres driver, you would connect to Yugabyte using Yugabyte driver. And as part of the driver configuration, you can define all these things, right? So in the sense, do you want to distribute your load across all the nodes in the cluster, and then discovery is something that's been taken care of by your driver, right? So you just have to set a property called load balance. Once you set that property, then all the connections that you create to the Yugabyte cluster would be equally distributed across the nodes in the cluster. And from then on, the driver would do the heavy lifting for you. So if the connection gets invalidated to one of the nodes because of the node leaving the cluster or some intermittent network related issues, it would automatically reinitiate that connection to the other surviving nodes in your cluster. Yeah, the configuration is pretty straightforward. You just have to set a bunch of properties to get the job done. Yeah.
Any other questions from anyone? Okay, looks like
right.
You don't have any further questions.
Yeah. Once again, I think if folks don't have any questions, I think we can wrap up this webinar. So once again, thank you very much for tuning in. So if you guys have any further questions or would like to know more about Yugabyte, please feel free to join our vibrant Slack community. So you'll be able to reach out to us as well. Thank you once again.
Thanks a lot, everyone.
Thank you everyone for joining. We hope you have enjoyed today's session and we look forward to seeing you again. Take care and goodbye.